Okay, so this ice sheet is going to give you a chance to play a little bit around and see some nifty things about some of the systems of equations that we have. So you should take a minute to kind of pause this video, or before watching this video, you should give yourself a chance to look at it and try to solve as much of the stuff on this as you can. And then kind of come back to here if you're running issues or want to check your work. Alright, so let's say we want to go ahead and find the solution to the following system of equations here. So we're going to call this a homogeneous system. This will come up every once in a while in the future, since the right-hand sides of each of the equations is 0. Archer's reduce this, so Archer and Eva are both cats of Dr. Hershey, who helped kind of create these notes. So her cats are going to show up every once in a while from time to time. So this system, if you put it into a matrix and get reduced row echelon form, you should be able to get this as the solution. So if you want extra practice, I recommend trying to get from here to here on your own, just for some extra fun. So what we can do is we can write this system as x plus 7z equals 0, y minus 3z equals 0. And notice that z has no leading term. So z is a free variable. So then we have infinitely many solutions, and we want to be able to go ahead and write this, kind of said this, infinitely many. So we want to be able to go ahead and rewrite this so that x equals negative 7z, y equals 3z, and of course z is equal to whatever the heck z wants to be. So we can write this as the set of all negative 7z, 3z, z, such that z is an element of the real numbers, or we could write it as z times negative 7, 3, 1, such that z is an element of the real numbers. And so here, instead of using z on these solutions over here, we're using s, and so we can take and represent x, y, and z by this vector of negative 7, 3, 1 times some s, where s is something in the real numbers. So that would be our way of representing our solution to the system of equations. We want to go ahead and look at something that's not homogeneous. So if we took and looked at the same equations on the left-hand side, but different numbers on the right, Eva, the other cat of Dr. Hershey, got this system into reduced row echelon form. And so again, z has no leading term, so it'll be a free variable. And so we can rewrite these as x plus 7z equals 1, and y minus 3z equals 1, which will become x equals 1 minus 7z, y equals 1 plus 3z, and z is still z, and it's still free. And so we have 1, 1, 0 plus z times negative 7, 3, 1. So for each of these, the first vector is denoting the constant term that is there. The second vector is denoting what kind of, for each x, y, and z, is associated with the z. And so here, that would be option C. So notice that when we're looking at those two questions, the relationship is that the answer to number 2 is equal to the answer to the homogeneous solution plus the constant vector. So that's just kind of nifty thing to notice. Let's take a look at question 3. So let's say we wanted to go ahead and determine the solution to this system of equations. And we end up with this as our answer. Well, what we end up doing is we get x plus 7z equals -8 and y minus 3z equals 3. This is starting to look familiar. So rewriting this, we'll get x equals -8 minus 7z, y equals 3 plus 3z, and z is going to equal z. And you can kind of think of it as being z plus 0 if that helps you see the constant vector portion. So the constant vector part will be -8, 3, 0. And the other portion will be -7, 3, 1 times z. Remember, z can be whatever we want it to be in the real numbers. So both option A and option C are going to end up working here. So the reason for that is here we don't have the right vector, so B's out. Here we have the right constant portion. And for this next part of the problem, the vector here that we have is -7, 3, 1 times some s, where s is something in the real numbers. Here we have 7, -3, -1. So notice that all the signs are flipped for this portion, but since we're taking anything in the real numbers to multiply it by, this is what's going to let us go ahead and use and have the same solution set. So that'll be kind of nice for us. Alright, so let's keep moving on. If we wanted to look at the matrix associated with the reduced row echelon form of A, the solutions to Rx equals 0 are going to be the same as solutions to Ax equals 0. This is true because the last column is all zeros. The row operations won't change them. And if we looked instead at letting R be the reduced row echelon form of matrix A, the solutions for Rx equals B are not going to be the same as Rx or Ax equals B, because row operations change this B vector. So when we do our row operations, typically what we're doing is we're saying we have A augmented with B. If B is all zeros, then changing this to get R will cause B, we'll call it B star, to be changed. Now if it's zeros, that doesn't matter. So the solutions aren't going to change. We'll get the same thing and everything will be fine. However, if there was something here that wasn't 0, when we do these row operations, this will be changed. So we have to be careful about that. Alright, so what is the value going to be of A so that this linear system is going to have infinitely many solutions. So in order to have infinitely many solutions, we want to be able to end up with something where we end up with a free variable. So if we take this, we can take row 1 and swap it with row 2 to get 1A, 4, 2, 6, 8. And then from there, we want to go ahead, and since we have a 1 here, we want to make it a leading one by getting rid of that 2. And so in order to do that, we'll take row 2 equals row 2 minus 2 row 1. And so we'll end up with 1A, 4, and 0, 6 minus 2A, and 0. And so in order to make this be a free variable, we need 6 minus 2A to equal 0. So that'll cause that to be a free variable. And so doing some algebra, 6 equals 2A, and A equals 3 will make this a free variable. Alright, so let's say we wanted to solve the system represented by this augmented matrix. So if we take a look at each of these equations, there's one of these equations that's going to matter the most. And so that'll be the equation represented by the third row. So this says that 0 equals 1, but we know that's not true. So this is going to have no solutions. And we want to go ahead and then represent this matrix based on this reduced row echelon form. But this isn't a reduced row echelon form. So I'm going to show us all a fancy trick. Fancy trick time. So if we take a look at this particular matrix, what we can do is in your calculator, so if you have a TI-84 Plus Silver Edition, other calculators will do this, and Octave Online can do this as well. What you can do is you can go to Second Matrix, and then go over to Edit, and you can make a matrix in your calculator and have it be put in a reduced row echelon form for you. So I don't know if I'm convinced this is in reduced row echelon form. And so what I want to do is I want to go ahead and I have 4 rows and 5 columns. And so I'll type 1, negative 1, 0, 0, negative 4, 0, 1, negative 3, 0, negative 7, 0, 0, 1, negative 3, negative 1, and 0, 0, 0, 1, negative 3. Alright, so if I want this in reduced row echelon form, I can go over to Math, go to RREF, and go type in our matrix that we just typed in A, and we can actually get this into reduced row echelon form using our calculator. So let me copy that down. We end up getting 1, 0, 0, 0, negative 32, 0, 1, 0, 0, negative 28, 0, 0, 1, 0, negative 7, and 0, 0, 0, 1, negative 3. And so here, if we're treating these as being our x1, x2, x3, and x4, what we'll get is x1 equals negative 32, x2 equals negative 28, x3 equals negative 7, and x4 equals negative 3. And so this will be our final solution. And so what we need to do, what we could do is we could do some of these row operations by hand. We could go ahead and take and add the correct multiples we need in order to get those. So I recommend doing that on your own for a little bit of extra practice, and you should end up with this as your final form matrix. Alright, now one more system for us to look at before we wrap things up on this one. So let's say we wanted to go ahead and rewrite this and solve this system. So first, let's put it into a matrix. 3, 2, 1, 39, 2, 3, 1, 34, 1, 2, 3, 26. And so what we want to do is we want to be able to get this in a reduced or echelon form. So the first thing we need is a 1 up here. Now the easiest way I think for us to do that is to switch the first and the third rows. So let's take row 1 and switch it with row 3. So what that does for us is it gives us the following matrix. 1, 2, 3, 26, 0, -1, -5, -18, 0, -4, -8, -39. Whoop! This is why you need to be careful when you're doing these row operations. So I'm writing off of a guide, which is helping me kind of keep everything straight. But it can cause you to make copying errors. So 1, 2, 3, 26. I feel like I just said in the last video, I will make a mistake on this before the semester's over. I did not expect it to be that quickly. Whoopsie. 34. At least I caught this one before I put out the video. That'd be a bummer. Alright, so we have a leading 1 now, and we want to be able to go ahead and get rid of the entries below the column. So what we'll do is we'll take row 2 and row 3 and change them by saying row 2 equals row 2 minus 2 row 1, and row 3 equals row 3 minus 3 row 1. So again, the reason we chose 2 and 3 there, because of the entries that were already there for us to work with. Okay, so that gives us the matrix I started writing up there. 1, 2, 3, 26, 0, -1, -5, -18. 0, -4, -8, and -39. Okay, so we eliminated the things below there. Now we would like for this to be a leading 1. Currently it's a -1, so let's just take row 2 and set it equal to negative row 2. This will give us 1, 2, 3, 26 for the first row, 0, 1, 5, 18 for the second row, and 0, -4, -8, -39 for the last row. Helps if I'm on screen. Okay, so we have our leading 1. We'd like to eliminate the thing below it. So we'll go up, do another row operation. We'll take row 3 and set it equal to row 3 plus 4 row 2. So again, I'd like to reiterate, you don't need to be doing things in the same order I am. However, you should get the same answer at the end, regardless of what you do. So row 3 plus 4 row 2. And so when we do that, first 2 rows won't change. So 1, 2, 3, 26, 0, 1, 5, 18, and 0, 0, 12, 33. Alright, so we want to go ahead and take this 12 and turn it into a 1. So what we'll do is we'll take row 3 and set it equal to 112, row 3. So we get 1, 2, 3, 26, 0, 1, 5, 18, and 0, 0, 1, 2.75. Alright, so we need to start working backwards now. So we've got our leading ones. Now we need to get things into reduced row echelon form. So in order to adjust row 1, we'll take row 1 and set it equal to row 1 minus 3 row 3. And we'll take row 2 and set it equal to row 2 minus 5 row 3. And so when we do that, we end up with a matrix of 1, 2, 0, 17.75, 0, 1, 0, 4.25, and 0, 0, 1, 2.75. Okay, so we only have, I think, one more operation to do, and that's to take this 2 and turn it into a 0, so we can get reduced row echelon. So in order to do that, we'll get row 1 equals row 1 minus 2 row 2. We'll end up with 1, 0, 0, 9.25, 0, 1, 0, 4.25, and 0, 0, 1, 2.75. And so reading off our solution set, get x equals 9.25, y equals 4.25, and z equals 2.75. And so our solution would be 9.25, 4.25, 2.75.